Right. Good afternoon. It's my great pleasure to welcome Professor Akyildiz for the Triangle Computer Science Distinguished Lecture series today. Professor Akyildiz is the Ken Byers Distinguished Chair Professor at the School of Electrical and Computer Engineering at Georgia Tech. And he's an IEEE Fellow and an ACM Fellow. He has a very long list of accomplishments and awards that I'm not going to go through because I'm certainly not here to listen to me. He is the editor-in-chief of 4 journals, Computer Networks, and he's Computer Networks, Ad hoc Networks, Physical Communication Networks, and Nano Communication Networks, which is an area of research that he pretty much launched on his own a couple of years ago, and which is directly related to the topic of this talk. I'm going to add just a short personal note here. 20 years ago, as a PhD student at Georgia Tech, I took my depth exam, which is kind of the equivalent of the qualifying exam for the PhD degree. And I was tested in 3 subjects: computer networks, distributed systems, and performance evaluation. Professor Akyildiz was the member of the committee that grilled me on the performance evaluation area. And this, in fact, is the reports on that subject that I prepared for my my exam, and it's beyond the feelings of nostalgia, right? There's it's very interesting to go through the technologies and acronyms that really reflect that particular age and the types of research that was prevalent in the late 80s and early 90s, including things like QE networks, ATM, DQDB, FDDI, ARQ, and so on. So without further ado, Professor Akyildiz will actually talk to us about technologies that we're going to be discussing the next 10 to 20 years.
Thank you, George. Good afternoon. Thank you for coming to my presentation at this hour of the day. This is my second real visit to NC State. I was here 23 years ago. Maybe many of you were not born that time. I was visiting Professor Harry Parris, who's a long-standing friend of mine, and also he helped a lot to my career in the beginning. I have to say thanks to him. Again, thank you. And he was a great man, and he's still a great friend of mine. It's very nice to be here. And also same thing with George. I was very happy to have him as a student on his committee. He was not my direct student, but I was serving on his committee. He took one of my classes. He got, of course, an A, and so I'm very glad that he invited me. So we have been talking since 3 years, and finally we realized this trip, so I'm very glad to be here and also visit some other friends of mine. So again, thanks to you all for hosting me here. So you see there are some things to explain here. So first of all, this nano stuff. So how does this come out? So 3, 4, 5 years ago, actually 5 years ago, some of my students were on the market, and they were complaining about that people are looking for nano people, nanotechnologies, and all these campuses are creating nano buildings, and everywhere, right and left, nano, and in Europe and then also in the U.S. So I was taking a shower. Mostly I get my ideas in the bathroom and in the shower. So I realized I went through the microchips technologies in the 70s. So suddenly I got curious when these nano devices are out, and they will be out soon, and they need to communicate, or they will need to communicate. So and I got curious, and then at the same time, this was like, as I said, 5 years ago, I received some visitors from Spain, from Madrid and Barcelona. They had some PhDs, and they came actually to my lab for sensor networks. I said, forget the sensor networks. Let's look at these new things. How can we realize this communication of these nano devices when they're out? So they were like not that excited, but then somehow I convinced them. So that's why we started to look at these nanoscale device communication aspects. And I always told them, number 1, we are not device people. Number 2, we are not chemistry, physics, or whatever. I will come back to those. We are communications people, and we want to look at the communication aspects of these devices. So now, then we start to work, and I have been, you see another title here, Universitat Politècnica de Catalunya. So this is another story that I have been in Barcelona, first time back in 1973 during Franco times, and I fell in love with Barcelona. So I was hippie that time, and I really loved that city. And then I used to go back and forth to Barcelona. And then the last 20 years, I established a good connection to the university people. And especially the last 10 years, I was going there every couple months almost. And then in 2007, I told them about this nano idea, that I would like to create a center. So they loved it, the president level and also the dean's level. And then we started this NTRICAT, stands for Nanonetworking Center in Catalonia. So in the meantime, we have at least 12 people, professors from medicine, biology, physics. This is a true interdisciplinary research. So we create that environment. We have funding from Catalonia. We will get funding from Brussels, like we passed the first hurdle for future emerging technologies from the European community. And so that's the story behind the Barcelona, and you see the logo there, NTRICAT. I also started the research here at Georgia Tech. We have also several people, several professors from different departments, and we also got some funding from NSF. So this is the background story, and here is this promotional second. We have 4 papers. The first one is the one that we worked together with these 2 visitors from Madrid and Barcelona, Fernando and Cristina. And so it took us 2 years to establish these research directions and topics. We published in the Elsevier Journal. And then the next paper story is, in the first paper we thought the only way to go is this molecular path, molecular communication. And then when I hired this Josep Miguel, who was at MIT for masters, again also from Barcelona, so he said he would like to go through the EM case again, because we thought there's no way we can do the EM case. So he realized that we can do it indeed. And so we wrote this roadmap paper taking the EM path. So, and then we also looked at some other issues like Internet of Nano Things, which appeared in Wireless Communication magazine, and then also try to reach out to the computer science community. So there is a paper that will come out in 2011, Communications of the ACM. So these are the the papers that I recommend you if you want to get into this field, because they're easy to read and understand. So the paper, the presentation will be based on these 4 papers, and I will try to convince you there are tons of very interesting ideas to to challenging problems to attack. So the nanotechnology is, it enables the control of matter at an atomic and molecular scale. So now, as you see here at this scale, on the right-hand side, there are so-called nanomaterials like carbon nanotubes or graphenes that they create these new properties which we cannot be seen in the microscopic level. So the objective is how can we exploit these properties of these new nanomaterials and create new devices and several applications which I will also present to you. So now you can see here these nanomaterials like graphene, nanotubes, and nanoribbons. In fact, you see these 2 names, Andrei Geim and Konstantin Novoselov. And I used to, since 3 years, I'm presenting these ideas. And I used to say, I predicted that these people will receive Nobel Prize someday. And indeed, in November, it was announced that these 2 guys who invented the graphene, they received the Nobel Prize for 2010. So this graphene, as you see here, is on the left-hand side, a 1/8 atom thick planar sheet of bonded carbon atoms in a honeycomb crystal lattice. So now you can see these carbon nanotubes like these. Of course, they are extremely small, like infinitesimal small, like smaller than hair even. So this is a folded nanoribbon, which was invented in 1991. And then graphene nanoribbons, GNRs, which are a thin strip of graphenes, which were invented in 2004. So now these nanomaterials have been analyzed in terms of electrical and optical properties in light of quantum mechanics. And then people are discovered that they have high current capacity, and also high thermal conductivity. That means they are extremely energy efficient. Everybody talks about green computing, green communications, right? So they're extremely energy efficient materials. And they have extremely high mechanical strengths. They are robust. And then also they are very highly sensitive. That means when you want to use them for sensing capabilities, they are a perfect match. So having all these fantastic properties can we create new era of devices. So indeed, from the batteries perspective, memories and processors and antennas, transceivers, we can create all these devices in the nanoscale. That's what these nano device people are trying to achieve. So now what these people do is, what I realize is that there are two ways, actually three ways that people are trying to develop these nanoscale devices. So the top-down approach is taking the device that we have now in the macro scale and then scale them down to nanoscale level and create these nano devices. This is called top-down approach. The bottom-up approach is, as you see here on this side, that use all these nanomaterials, create antennas and batteries and processors, memories, etc. From scratch, from bottom up, you create nanoscale devices. And then there is another path, which is like the biological path, we call it. So now go to the nature and then mimic the nature. Like I will show you some of these cases. Like the human cell, for example, has mitochondria. Can we use that as a battery, for example, power source? And then the hormones and DNAs and proteins. So use this nature or natural sources and mimic them and create nanoscale machines. It's called like biologically inspired nanomachines, they say it. Okay? So these are the three ways, as if you say like top down, bottom up with two cases. My personal opinion is that this bottom-up approach, biological with the nanomaterials, will like kind of hybrid solution will survive over the next 25 years. So it's a hybrid way to go. Okay. So now what we will discuss is there are these two paths that we will be looking at, from the nanomaterial-based nano devices and then the biological nano devices. So as I explained to you that we are not a device person, we are not developing these. Here are the simple example that I want to discuss with you. A simple nano device, for example, it has sensors here, nanosensors, nano actuators, nano antennas, nano transceivers, and processor. And what you see as brush here is the battery part. We will see that. So now let's go through all these components and then explain to you how these nanomaterials are being used so that these devices will be developed. Nothing is existing so far. If anybody tells you that there exists a nano device, it's not true. So they are still developing these components. So it's a long way to go. So now one of the challenges is when these components are being developed, how will they be put together? Like as you see here, they are like somehow integrated into one device, right? So how can we do that? One of the ideas here is called DNA scaffolding. So now you have these DNA strains here, as you see here, adenine, guanine, thymine, and cytosine, and then you can see that they can match each other. And then now what you do is you take these nanomaterials, for example, you put these DNA strains, and then you glue them somehow. And that process is called DNA scaffolding. So accordingly, they will put these devices or these components together through the DNA scaffolding, but the research is still continuing. So this is not, done deal. So let's look at all these components separately. So there are these nanosensors, like in the physical nanosensor, meaning, as you see here in the middle again, is a carbon nanotube. If there are external forces, they can somehow sense that and measure it. Or chemical nanosensors, like gas molecules that can be sensed by these chemical sensors, or biological nanosensors, like the antigens and antibodies can be somehow sensed and evaluated by these sensors. Here you see the battery part. These are so-called zinc oxide nanowires, and you can see the scale like 2 micrometers. And I have a colleague at Georgia Tech, Z.L. Wang, who is the guru in the world for this type of technology. He's developing zinc oxide nanowires. Okay, so like you can see that they will be creating this energy, the power sources for these devices. And of course, we'll have infinite amount of, hopefully, infinite amount of batteries, energy sources through those. So the nanoprocessors, most of the latest laptops have already nanoprocessors, the latest ones. And they're like the 32 nanometer transistors, like 220 nanometer technologies around the corner. And you see here under the microscope, this is from the University of Manchester, that was back in 2008. It's a 1 atom, but 10 atoms, 1 nanometer transistor here, as you can see here. So the nano memory is, so now the objective here is, how can we store a bit in a single atom? Okay? So that's the objective. So Richard Feynman, if in case you never heard of the name, please go to lectures like YouTube and Feynman lectures. He was an interesting fellow. He's actually the father of the nanotechnologies. You know, he's a 1965 Nobel Prize winner. So in the '59, he made a very famous speech. So that's the guy that you should really he has books and all that stuff. It's funny books. Very interesting fellow, Richard Feynman. So he said that he gave an example in 1959. 5 by 5 by 5 atoms were used to store a bit and to avoid inter-atom interference. So now currently we have 125 atoms per bit. So now the DNAs, there are some people in computing, they are looking at using DNAs, they have 32 atoms per bit. So now we would store a bit in a single atom, like as you can see here. So then we'll have this gigantic memory space. So for that, people are using devices with gold nanomemories or magnetic memories to achieve this objective in terms of nanomemories. So now nanotransceivers are again under development. We want to do all of these, like the ones that we know in the classical communication, baseband processing, frequency conversion, filtering, etc. And we can also use graphenes to develop these transceivers, nanotransceivers. In fact, in the proposal that we have project in Barcelona, we have people from Germany. They are looking, they are doing nanotransceiver device development and nano antennas. So they have some success, but it's not like out there that you can purchase them and then use them. It's not like that. So it's still under development. So now it's interesting. We'll come back to this. So these transceivers will be operating in the terahertz band. Okay, so now most of you know like gigahertz or megahertz, but now we are moving up to terahertz band. I will revisit that issue. There are also activities about nano antennas. So again, the people are using graphenes, okay, to develop these nano antennas, like using a single carbon nanotube or a set of them, or using a single graphene nano ribbon as a nano patch, or atom precise antennas. Like here, this was from our with my student. This is just a design, as an idea about like nano patch antenna, as you can see here. We propose model and analyzed. This is the kind of like the graphene that we see here, and it's like it's a patch antenna. And then we analyze this and we evaluate the performance, the contact resistance, quantum capacitance, and kinetic inductance as a function of different design variables like ribbon dimension, system temperature, and system energy. And it works on the paper, of course. We still need to somehow design and test that. So what did we learn from this study of the nano antenna? So that using these nano antennas, the electromagnetic waves will be radiated in the terahertz band, like 0.1 to 10 terahertz band. So that means we have new opportunities for EM scale communications. You cannot use these existing communication protocols that you may know from these classical textbooks and research and all that stuff that is out there the last 40 years. Forget them. So I will also convince you through our results. So now we go to the terahertz band, Now we need all these new solutions. Okay? So I will come back to this again. So I hope I convinced you about what's happening in the nanomaterials, like people are developing these components separately, and then it's still going on. So now let us look at the biological part, and again talk about modules separately. Okay? So now you can see this is a human cell that we can use this as a most natural nanomachine or nano device. So you see, like, nucleus could be seen as a processor. The DNA could be seen as a memory and processor. And then vesicles could be used as the message containers. Receptors can be used as receiving, like receivers. Gap junctions can be used as the relaying nodes, like the relaying parts. And then mitochondria can be used as the power source. And then flagellum is for the navigation of these cells. So now the challenge here is, how can we mimic all of that and realize these nanomachines? That's a huge challenge you can imagine, right? So let me go through these separate items again. Like the cell gains useful energy by combining glucose, amino acids, fatty acids, and oxygen. And then it obtains energy which is used to synthesize so-called ATP, or adenosine triphosphate. Okay? So here is the energy source in the cell. It's under microscope. That's the typical mitochondria in human body in the cell. So it pumps, it gets all these glucose, etc., acids, and then it creates energy. Okay? So this is the way that we could somehow mimic that and create energy. And indeed, this is already almost to be realized, that maybe some of you read it somewhere, that there will be soon sprays that you will spray on your cell phones. It will charge energy. That's exactly from this technology. Okay, so like spray the energy, and the battery will charge the energy, and then it will recharge itself. Don't say where is it now. So just wait, please. Okay, but this is already very close to be realized. So these are also some of these biotransistor. It was the latest IEEE Spectrum magazine when you receive it. Okay, the main idea is to design a cell in the same way we design a silicon chip. Okay, so now can we create these biological transistors like these here, based on protein synthesis from DNA. So like you see these DNA strains here. So now somehow we will synthesize these and then create these proteins. Okay? So the outcome of this process is called synthesizing, will be all devices which we are producing in silicon chips may be reproduced from as cells, like living organisms or living circuits. And accordingly, we can create new functionalities from these new biotransistors, okay? And like we can control production of chemical substances for drugs, etc. Okay? So now we can also do this DNA computing. There are a lot of computing people since 1995. They are looking at the DNA computing issues, like how can we create more complex architecture using these biological transistors, like for example the CPUs. Can we use this ATP that I just talked about as, like the energy source, as fuel, and which can help us to run these devices? And also, can we do all this parallel computing that these people are trying to do since 1995, as I said? So these are all question marks. Now, transceiver, as you see here, is the cell will act like a transmitter, right? You can see it synthesizes and releases molecules. These round things are molecules. They are released. You can see through. So now there are this inner concentration, they are called, and then the outer concentration, like they are leaving out, like these here. And so now these molecules can be seen as the message containers, and the packets will be somehow put on these molecules, and they will be released to the channel or to the air, right? So they will float. So this cell will be created as a transceiver, and then this transceiver will release, like the cells release the molecules, it will release this package or messages. Same thing, reception process. We will come back to this. It's called ligand recepting process in these biological terms. Now, this is the cell which is acting like a receiver. And these molecules are floating around, and somehow they will be sucked by these ligand receptors, they called. So some of them, of course, they float around. They don't reach this receiver, but some of them will be reached, and they will be received, and they will be evaluated, of course. Like, receiver receiving these messages and packets, and then it decodes them. Same thing here. So this is the way that we will mimic and try to realize these, biologically inspired transceiver and receiver, for example. Here is another example with the antennas. In the nature, all the animals are communicating through pheromones. Right? So now this is an antenna from a moth, this little animal. So the pheromones are coming, the moth pheromones, and they are indeed received by this antenna of this moth, and then they will be evaluated, and then somehow will be converted in the moth life. That what is meant in the through the pheromones. All the animals like tigers and elephants, etc., they do this pheromone communication, and they all have antennas, right? So now the challenge here is how can we use these natural antennas and create our own antennas that we can use in the nanoscale. So I hope you see these challenges for the nano device people. Okay, so this is not my interest. So I'm still not there with the communication problem. So we're still talking about in terms of device issues. How can these device people come up with new ideas, like transistors and memory and transceivers, receivers, antenna, etc. So, and of course they will be put together, and then the nanoscale device will be created, and then they will be connected. So they will be created as a nano network. So either EM-based nano networks, like using these nanomaterial components, these devices, or the devices that they were developed using the biologically inspired components, and they create a nano network. So now we are now more in our domain, meaning in my domain or in the domain of the seminar. So now some of you are asking, what are the applications? So when you see these applications, it happened to me like a couple of people left because they thought this is too much science fiction. It is not. So here is an example. You will have, there are these body networks, right? Body sensor networks. You were leaving now? Body sensor networks, this is different. These are more like you will inject these into the body of the humans. Don't say, whoa. Okay, so these will be like blood cells. Like, don't forget, these are very infinitesimal small, like hair. It will be injected kind of drug, and they will create any network. Like here, for the brain cases, I will show you some applications. And for the heart, it depends again for what reason we will be injecting these these devices that they will run in our body, and then they will observe the body. They can detect tumors and help you alarm anything that you may have, viruses. Either they will fight it, like these blood cells, the existing blood cells we have. Additional blood cells, they will do these collective, cooperative attacking, quorum sensing they call them. So then they will try to solve the problems. If not, then they will alarm outside, saying there is some problem inside of the body. There are also neuron networks. In other words, our cells in our body, they have electrical and molecular links, and they communicate, and they indeed create a network inside our body. Okay, so now if somehow we create these models and analyze them, we can try to understand how in vivo networks of neurons work. And then we can accordingly create diagnosis and treatment solutions or tools for example, brain pathologies or heart problems or some other medical applications. I will come back to it. Okay. Here, there are heart monitoring networks. Like the heart muscle cells are called cardiomyocytes. Okay. So now they are interconnected for heartbeat synchronization. They use molecular and electrical communication, And we can model this. In fact, we are submitting another proposal to Brussels to look at that with some medical people in Europe, to model this and understand the communication of these cardiomyocytes, and then create some diagnostic tools as well as disease treatments for the heart problems, for example. So the list is very long in the medical applications, like these, diabetes people, glucose level measurements, sodium and other ions monitoring, cancer monitoring and control, smart intrabody drug delivery, like all these problems that we already have now, Alzheimer's, epilepsy, depression, that will be easily detected and they can be controlled. Any infectious agents detections like the malaria, etc. So the list is very long. So the bottom line of this slide is, including for myself, please hang in there. Our lifespans will be over 300 years. So if these things really will be realized. Okay. So now there is another application, the bacteria communication. Okay. The networks of bacteria, they communicate through molecular signals. And also these bacteria have this cooperative network behavior, and it's called, in the biology, it's called quorum sensing. It's very interesting. Biology people, I said I work with those people. We had tough time in the beginning with the language and explaining things to each other, and they also fixed my pronunciation of these biological terms. So now you can see they can program the bacteria. Okay? They can genetically engineer these things, and these bacteria can act like nanomachines. Okay? And then also they can inject some DNA information on this bacteria, and the bacteria move, and they can move and they can be navigated. But it's very interesting. I don't know that we have people here. There is this so-called delay-tolerant networks. And now we used to do that in the 90s with my group on the satellite, like the interplanetary internet, with all these long delays, 8 minutes to 40 minutes to go to Mars, the propagation delay. Talk about delay-tolerant networking. Bacteria network. Bacteria, don't laugh now, please. 1 centimeter, it needs 4.5 hours. So that talk about delay-tolerant networks. So now, really. And then it's another thing is they move, they tumble around, and they somehow, like 1 centimeter becomes like 20 meters, but it comes back here. It converges to the destination. But it's really fun to watch them, how these biology people working with this bacteria. So now, what can you do with these bacteria, right? Because you can program them, right? You can, genetically engineer them, etc. You can develop new antibacterial drugs. But also, the list is really long. You can create these biofilms like bacteria colony. You can do pollution control because these bacteria eat a lot of things, right? You can throw them to these environments. They eat everything, and then they can clean up a lot of things like these waters, like these polluted waters. They can clean them up. Or pipe cleaning. So there are a lot of these kinds of applications of the bacteria. Here's another thing about chemical attack prevention. So maybe some of you are doing sensor research. When you do sensors, microsensors, and a chemical attack happens, good luck. Because until the sensor detects it, you're dead. But with nanosensors, they have very high granularity of the sensing capabilities, so they can immediately capture that and then they can alarm. So that's a very good application in terms of chemical attack prevention. Okay. Then here is another thing about, everybody talk about gigabit, Ethernets and all that stuff, So now with all these new applications, we'll be able to support terabit per second links in the wireless domain, again, with these technologies. Okay. And also do not forget all these future devices will all have nano components inside. So it doesn't need to be everything small, right? Because I told you they already have nano processors. They will have nano memories and nano transceivers, nano antennas. So all the components will be nano, and accordingly we can go to the terabit per second. So, and also the access networks. It will be terabit wireless access networks. I call them 6G or whatever, 8G. So like you can see, all the accesses will be on the terabit per second link. So terabit wireless personal area networks, like you can see, like very short distances, you have all these different devices. you can go back and forth between these devices through the terabit links. And then also, the future internet, this is again at least 30 years beyond, like, many years to come, all the routers and, all these gateways, everything will be having nanoscale components. So, of course, we will still have micro routers and all that stuff, but over 50 to 100 years, everything will be, replaced by the nanos. So this will also be the kind of future internet after next, right? So everybody talks about next internet. Here's Internet of Nano Things. There's Internet of Things, but also Nano Things. So you will have all these nano components, as you can see here, inside of the body, outside, and all the areas. And they will communicate, and they can also go through the Internet and have all this kind of Internet of Nano Things realization. So I hope you have seen all these applications. Some of them sound very futuristic, but we are talking about 50 years, beyond. It's not like 3, 4 years, 5 years. So these devices not even existing so far. So now we do all these, preparing the foundations of these studies. So now, after applications, I want to go back and revisit these terahertz band for electromagnetic cases. Okay? So this is the paper that we try to understand how the terahertz band behaves. When these nano devices are communicating in the terahertz band, what can we expect? What can we do? So we have this paper which we published in ICC 2010, and the journal version appeared in 2011, where we developed a total path loss and noise models for EM communication in terahertz band between 0.1 to 10 terahertz. What we did is we studied molecular absorption by means of radiative transfer theory. We also developed some power allocation schemes and also computed the channel capacity. So you can see here the total path loss. It's a long formula. I don't want to go through all of this. Spreading loss plus absorption loss depending on the frequency and distance. Okay. So now the spreading loss you can capture from like this formula here, frequency, distance, and speed of light in vacuum, and absorption loss, the same thing here. But then you can start to see all these, terahertz band level, like temperatures, reference temperature, system temperatures, etc., molecular, volumetric density of each gas. All these terahertz band peculiarities are in this absorption loss. What is the peculiarity of the terahertz band is when you communicate in the terahertz band, you have all these water vapors, molecules, that they create noises. You do not see those when you are in the gigahertz or megahertz band. But when you go terahertz band, you have very, very fine granularities in the air that affect your signal propagation, and they're all captured here, like system pressure, etc., temperature, volumetric density. So we captured this in this formula. And then, accordingly, we also have molecular absorption noise formula here. Again, you can see same of these channel effects, the air effects on the signal propagation. So what is the uniqueness of the terahertz band with the studies of these formulas? That, as I told you, the terahertz channel is seriously affected by the presence of different molecules in the medium. Okay? So the high molecular absorption attenuates the traveling wave and introduces noise into the channel. Those noises we do not see in the gigahertz band or megahertz band, as I told you. So now, when we depict all of this results here, then you will see what I'm talking about. So now, this is the total path loss formula, and these are the frequency terahertz from 0 to 10 terahertz band, and then this is the distances between the devices. And then you see this red area is, there is no way that we can communicate. The path loss is almost making impossible to communicate. So like when you go to 1 kilometer distance between two devices, the path loss is awful. So you cannot communicate. So now you can see around 1 meter there are some some windows you call them, that you can sneak your traffic through. So the path loss is somehow acceptable. But when you go down to the shorter distances, you can somehow take care of those because path loss doesn't affect the communication. So what is the lesson we learn from here is that we are distance limited. So we have to keep these distances between these devices very, very short. So here we see about molecular absorption noise, the same thing with the distances. We got all these noises that we did not see in the other, like giga and megahertz bands. So what did we learn out of this study so far? So a terahertz channel has strong dependency on the transmission distance as well as the molecular composition in the air, in the channel. So then the worst enemy of the communication of the signal traveling is the so-called water vapor molecules. So that accordingly, when you go too far away, then the signals do not propagate because these water vapor molecules will affect the signal propagation. Then we have these path losses. So now the advantage of this here is we have gigantic bandwidth, like talk about terabit per second. But then we have very short distances, like around meter. So now, of course, this is one of the challenges. How can we, expand the distances between these devices? So after this channel modeling analysis, we also have a scheme which we call this time spread on and off keying mechanism. So now, how can we somehow communicate between these two nano devices? So we have this idea called femtosecond long pulses. So we send femtosecond long pulses and using this time spread on and off keying mechanism. Okay. And then we have these studies that we did. Here you can see in the time domain and the frequency domain about these femtolong second pulses. As you can see here, it's a very short, very, very extremely short. It's like it doesn't reflect it here. Femtosecond long pulse in the time domain, and then in the frequency domain you can see the best performances in the 2 terahertz. So like we can operate these networks into 2 terahertz and use this femtosecond long Gaussian pulses. So why? Because these are very simple and energy efficient. Plus, these technologies are used for the current imaging in the airports. When you go to the airport, people were complaining that they can be seen naked. That's exactly this type of technology, like this nanoscale imaging that can capture everything, right? So that's already something out there that we may try to use it for these on and off keying ideas. And also these pulses are 3 orders of magnitude shorter than this. It's already this ultra wideband technology. Some of you may know because you can say, oh, that's the same thing. It's not. We're losing femtosecond long pulses, by the way. So you can see this time spread on and off keying. The ideas are here is, so we send each time we have one, we have these femtosecond long pulses, and then we wait this amount of time, TSS, and then we send another one. So now the logical 0 is encoded with silence. If it's 0, we don't send anything. We don't do anything. So accordingly, we will not consume any energy, right? You can see here. So, and then if there is no activity, then the receiver will think that it's a 0. It will just decode that as a 0. Okay? And then these femtosecond long pulses have the duration 100 femtosecond, and the energy consumption is less than 1 picojoule. So you can imagine how effective this is. Of course, when we have this, then we need a new mechanism for encoding and decoding. So you cannot use this existing encoding and decoding. It's impossible. Even without this, it's the capacity of these devices cannot handle that. Okay? So then we can have all this new ideas about if we send more zeros than ones, then we can save more energy, and being silent, we can avoid all these channel effects, and then we can try to optimize our performance. However, we need according schemes that will create more zeros than ones, still get our information to the destination, right? So now we have these new coding schemes that will appear in ICC Kyoto. We went to these old low weight ratio codes, okay? We modified it a little bit, and a little bit meaning a lot, but anyhow. So we use these low weight ratio codes. These codes are not your classical error correction codes, but these are more like avoidance, like how can we avoid errors before they happen. So there are so-called low-weight ration codes that we are using for this. It's just a suggestion. It doesn't mean this is the way to go. It's just a suggestion. So what did we learn about these studies? And then what else can we do? What else are the open questions about EM-based nanonetworks? So we need still research for accurate channel modeling. Okay, I showed you one model that with all these absorption, etc., the total path loss, but we need much more detailed assumptions, and then somehow relax some of the assumptions we did. So although I check marked them, but that doesn't mean it's done. So we need this. We suggested femtosecond long pulses using time shift on and off keying, but that doesn't mean we may not need some more new ideas. Somebody else can come up with another idea. Same thing with encoding techniques. We said these low-weight channel codes, but can we find something else? New MAC protocols, like my students and with the Barcelona people, they did this PHY-LAME, is a physical layer affected TS, like time shift on and off keying with the MAC protocol. But again, that's one suggestion. That's a long way to go. And all these things that computer science people are interested, they're all open. Okay? But do not make the mistake that I really hate, that taking the existing routing and MAC protocols, etc., just modify them and put their nano and then say, here's a nano MAC or nano routing. Don't do that, because this beats the purpose, right? It doesn't help us to advance the technology. So please don't do that. So think clear mind. And also, again, some people say, oh, you are still going back to the classical way of TCP/IP, whatever. I just showed this maybe to convince some of the people that they are used to the old-fashioned way. Maybe we don't need all of this. So, but that's why we need to start somewhere, and then we can come up with something. I call this cross-layer, or maybe some new name that we will just have a simple software that will take care of these communication. So I don't know, but I'm just showing you that you can write new papers, but maybe something totally new. So that we don't need to have all this, old-fashioned way of doing things. New energy models, and then of course, what else can we do with applications? And the interesting thing is, terahertz band is still not regulated. Okay, this is not science fiction. There is an 802.15 terahertz interest group. Okay, it's IG terahertz. They meet every 2 months, and they are looking at all the issues. They don't use the word nano networks. Okay, they just use terahertz band scale communication. So like 300 gigahertz to 3 terahertz. Some of you may know about 60 gigahertz wireless local area networks. They are nothing. I mean, these are more interesting cases. They are nothing meaning, I'm not belittling it, but these are more interesting cases. And there's the website that you can go and read it. And we did also some contributions here, like last time in Dallas. Okay. So now I showed you about EM part. Let's go to the molecular case. Okay. So I would like to make a very strong statement here. That is, believe it or not, all the empires have limited lifespans, as you know. When you look back in the history, all the empires had 80 years, some of them 300 years, but always a limited lifespan. And information technology era is coming to an end. It started in 1950. Believe it or not, you will observe. We are very young people, so I hope you will remember me. So this is fading out already. I mean, you guys talk about Facebook and all that stuff, YouTube. We're talking about information technology, right? So this is fading out. And I put here very optimistic 2030, 2040, but 2020, and then it will go downhill. Okay? So the era is molecular technology. So all the new ideas, all the new discoveries will be in the molecular world. And it's already started it. Now I put here 2020, but it's actually, it already started, all the molecular technology, like DNA technology, for example, right? So do not forget this. So that's why a lot of departments, biomedical engineering or biomedicine, bioinformatics, that's not, joke. It's really true. There is this future there. So it's not wasted money. So here is, again, from the communication perspective, how can we look at these nanomachines and look at from the molecular world and how these molecules will be incorporated package messages, and they will be floating around, and then they will be received, right? So how can we realize that? So the big picture looks like this. So people are not sleeping, actually. They're, especially the Japanese. Wow. So they're very active. So a handful of people in America, a handful of people in Europe. So the Japanese are pushing, also companies, and also in the U.S. So the more you get into, the more you will be, surprised how much work is being done in the background. So now we also expand this as we learn more and more. So we have distinguish between three ranges: short range, medium range, and long range. And look at the ranges: nanometer to micrometer between two devices. Okay, and then medium range, micrometer to millimeter, and millimeter to meter. First time we thought, when we use pheromones, when you go to animal world, sometimes elephants can get 20 kilometers the pheromones. They can smell that and they run, right? But now we fixed that because it's impossible to kilometers, so we put the meter. It's maybe still a little conservative, but that's meter distance. So now we also expanded it, there's this wired short-range communication. They use molecular motors. And the wireless, they use ion signaling, especially calcium signaling. These are all from the nature, by the way. And then the medium range, there are so-called flagellated bacteria. I talked about bacteria a little bit, so we can use bacteria. And then there are also so-called catalytic nanomotors or nanorods. These are very, very small, nickel, platinum, gold, very, I cannot show it even. So these are kind of like nanorods, they are called, or robots. So they are also called catalytic nanomotors. So that's medium range. Long range, you can use axons behavior from our body. There's these axons 1.20 meters here. And then, or capillaries like our heart, all these veins, and then pumping in, somehow, mimicking that. Or wireless pheromones or pollen and spores. How can we use those? So what I will do is I will go through some of these here and then point you out all the challenges, okay, from the communication perspective. So let us look at the molecular motor. What is a molecular motor is, as you can see here, it's a real picture. It's a protein. It looks like a devil, right? And in fact, there's a protein or a protein complex. And it's running on these nanotubules, like this here, microtubules they are called, 25 nanometer thick. And they create these wires, right? So wires. So now when you look at this big picture, they have this structure here. These molecular rails, right? And then these molecular motors, and then they will put information. These red dots are somehow we will, nano machine will create these messages, will put these messages in these molecular motors, and then they will be released and they will walk. Very, very interesting. You can also observe in the microscope with the biology people. So they go 1 foot, ahead and then 2 feet back, and then, so back and forth. So it's very slow, and of course that's why we have very short distances. And another problem is that they detach themselves from these tubules. When it's too far, they don't stay too long, and then they, we lose them, right? So we lose the message. So now, what are the details here in this structure? They have these microtubule, or this rail that I told you is 25 nanometers. That's the vesicle cargo. That's you can put all the information. The ankrine, spectrin, etc. So with the dynein, it's like the walking, the legs. So this is the protein complex, and then we will use this vesicle for the messages, and then put them and send them in. So what are the challenges here? Right here, that's one of the challenges. How do we encapsulate the information? Well, we can maybe use DNAs and then form the messages and then put them into the cargo vesicles and then transmit them, right? But that's all challenge. How do we do that? So now you can see all these classical steps of communication that are all open. First of all, how do I select the right molecules or molecular motors or molecules, and then which will represent my information, kind of like message creation. Then how will I transmit them? I put them in the molecular motors, and they will moving on these microtubules. And then also when they are received, how will they be removed, that information from these from the vesicles? And then how will we make sense of the whatever is received? Right? The receiver must somehow decode them and understand the value. Okay, so calcium signaling is the same way. They are using calcium signals. There are so-called gap junctions here, as you can see. And the steps are the following. How can I encode the information in calcium ions? And how do I initiate the signaling? And how do I propagate these calcium ion waves? And then how they are received by the receiver, and how will these calcium ions will be decoded and evaluated at the receiver site. So these are all open questions also. What are the problems of these short distance cases? The velocity is, again, very slow, 500 nanometers per second. And they also, as I told you, they detach themselves and we lose them. Okay? And most importantly, very, very, very long communication delays and very, very short distance, as you have seen in both cases, molecular motors and calcium signaling. So we do the same thing with the bacterial communication. As you see here, this was another lady from Barcelona. We did this work. We published in JSEC, May 2010. So this is the bacteria. It's an E. coli bacteria, by the way. You have all these the flagellas, rotary motors, and plasmid. Nucleate and pilies are for sensing. So you can get the information, inject here, and then navigate this bacteria and move around, right? So from one end to another. So these are the 2 micrometers long and 1 micrometer in diameter. So now let me jump to we don't have time to explain all of this. So all of these issues again are open. So how do we take the DNA packets, okay, and then we will inject them into bacteria or that cytoplasm we call it, like in the nucleus, that one. Can we use plasmids on bacteriophages or bacteria artificial chromosomes? And then how they will move. They sense gradients of the attractant particles. They sometimes cooperate with each other. And they move towards the direction and finds more attractions. This process is called chemotaxis process. Okay? And then the receiver releases attractants so the bacteria can reach it. As I told you, they also move around, tumble, but they always converge. That needs to be also mathematically proven that they will reach the destination, and the destination will extract the information, maybe using restriction endonucleases enzymes, for example. Okay? Same with the pheromones. It's very interesting. We have to also look at different types of pheromones, like in the animal world, right? So like specific pheromones can be only received by the specific animals or receivers, right? So now we have to somehow create the right pheromones and then inject into this, either air gases, meaning air, or liquids. And then the pheromones are diffused in the medium, and then they will be received by the so-called ligand receptor processes. And then that information will be somehow decoded, understood what is meant through these pheromones. So now we come to the last 5 minutes, right? 5 minutes. So this is the big picture. What else are open? So first of all the design people, that the machine designers, they will develop these nano machines, biologically inspired machines, and I hope they will come up with these existing nano machines in 5 years. Then we need modeling tools. Like you can use, some of you are doing King theory, but people are using automata theory models here. There are some Europeans or Japanese. They use automaton models like cellular automata, Mealy automata to model these nanomachine behavior. So nobody uses King theory or stochastic models. And then according to simulation tools, our Barcelona people are developing simulation tools to inject into NS3, which is the part of publicly available simulation tool. So now on the right-hand side, you see architecture and communication protocols. I gave you some examples in the EM case. The same thing in the biologically inspired case. These are all open questions. How do we beat the distance problem? And all the other challenges, of course. Come up with the architectures, connectivity, etc. And then the other thing here is, who wants to be next Claude Shannon? So we need a new information theory. So now what we did is we tried to work on this a new information theory model like, capacity formula and also this path loss and noises. So we looked at, transmitter, channel, receiver, and then also the noises. What kind of noises do we have in this molecular communication cases? Okay. So this is the paper that we published in JSEC in May 2010. This is another student of mine, PhD student from Milano that I hired. So we did the Massimiliano Pirobon. So what we do here is we process this emission process, how these molecules are created and released, and how they are diffused in the air. Like some of you may know about Brownian motion, like from the physics, like, there are these Adolf Fick's law 1 and law 2 we use for diffusion of these molecules. Of course, we convert them into our environment, like particles, as you can see, are moving, and then they are received by the receptors and the reception process. So what's happening end-to-end delay and path loss, for example. So we did what the study is that, again, there were a bunch of challenges, of course. How can we model and mathematically capture these things and analyze it, right? So I don't want to go through all of this. We don't have the time. But the formulas are the attenuation formula and delay are like, they look like this, all of transmitter, channel, and then receiver. And then, of course, all these have a math here from all, from transmitter channel perspective and also from the receiver perspective, showing what's happening in terms of delay and attenuation. So then the other issue was here, what type of noises do we have? Okay? So it's very interesting. On the transmitter side, we have particle sampling noise, because what happens is when you are creating these in the continuous domain and when you sample it in discrete times, so that gives you some losses, right? Because you're sampling that in the discrete levels. So that's the noise that is injected in the transmitter. In the propagation, it's called counting noise, because they're all moving around. Some of them are lost because they took different directions. Some of them are elastically hit each other and then they move and they reproduce themselves. So they're all additional noises that we capture here. And the same thing in the receiver. Some of them are received by the ligand receptor, but some of them cannot be received successfully. So some of them are lost. And there are, again, additional receiver losses. So we have these three types of the noise problems that we also captured. So we had this, the first two, we are having this paper in transaction signal processing in June 2011. And then for the diffusion-based noises, and then for the receiver side, we have also another work that it's a lot of mathematics. I skipped those, and which will also appear in transaction signal processing in fall 2011. Okay, and so again, we don't have the time. So now the question here was also, how can we rethink about Shannon's theory? So what is the entropy here in this domain? And then also, can we redefine the power consumption? So we have this paper that we I will present in Infocom in Shanghai. So we wanted to somehow revisit the Shannon's theory and try to find out the theoretical maximum achievable information rate when we use the molecular communication. So what we did is we took the information theory that we all know and we combined it with thermodynamics. And then we also assumed that because we are trying to find the maximum value, we apply the molecular communication to ideal gas systems. Like everything is like perfect, right? Ideal gas environment. And then we compute information entropy and equivocation from thermodynamics entropy. And then we relate the information single energy to the enthalpy of the molecules which carry the information. So what did we obtain? We obtained a closed form expression of the diffusion-based molecular channel capacity, the maximum value, depending on the bandwidth of the system, the volume, temperature, and the number of molecules, as well as the transmitted power. So the formula looks like this. So again, we don't have the time to go through all of this. So this is the capacity that we can achieve through the molecular communication. I wish I had more time. But anyhow, what are the research challenges still? So I showed you we have this end-to-end physical model, which I presented to you, but that's all with these generic assumptions. So now I also presented you some particular ways of communication, like molecular motors and calcium ions, pheromones, and bacterial communication. So how can we use our generic basic model and convert them into here? Either, we can just simplify it, or you may develop a new model in terms of end-to-end, like delays and attenuation, etc., for this particular communication paradigms. And then what are the new modulation schemes here? You cannot use these classical modulation schemes. Like, you have to look at the concentration issues, chemical structure and encapsulation. And then what are the interference? Like we talked about noises, right, from the transmitter and the channel noise and the receiver noises. But then what happens if you have multiple users and they somehow interact with each other, and then they will somehow create also interference about each other. Think about everybody is creating these molecules. Somehow there will be several types of different molecules, and they may interfere with each other, and there will be additional noise factors, right, interference problems. And then another issue here is, again, you go back to your classical networking, like molecular MAC protocols, right, and then molecular routing layer. What is the routing, addressing here, okay? And then molecular transport layer, redefine reliability. But again, please do not make that mistake and say, here's a molecular title and then I have a new paper. So don't do that. And again, I just put these as placeholders. That doesn't mean we have to do these things. So we may come up with different way of communication. So of course, then the next question will be, when they are developed all of this, the micro world will still exist, right? I mean, we cannot wipe them out. So there will be kind of like this optoelectronic bottleneck in optical systems. It will be another bottleneck between nano world and micro world. So we need more procedures there for the gateways. That's another subject, Of course, don't ask about security, please. Because I know a lot of people ask me the security. What about security? It's too far out, so we're not there yet. So now, what's the objective here is, what we are trying to do is, not me, also some people in the world, like we look at these issues and these issues from the communication perspective, okay? And when you understand more and more, and then I think long way, after 10 years, I think we will go and more understand the hybrid case, like some of these nanomaterials mixed with some of these ideas from the nature, and then somehow come up with these new communication technologies. But first we need to understand, all these separate areas and then come up with the solution. So here is a journal that I started in March 2010 to promote this area. So it's second issue now, second volume. So we have relevant papers from different areas. It's not just computer science EE. So from all around the world. So we have the first international IEEE workshop, which is with IEEE Infocom conference this April. We got 20 papers. So it's like full program, which is really a very nice development actually to see that people are working. We have also these every year. This is the third Nano Networking Day in Barcelona. We do it just before the San Juan Day. San Juan is the big party in the city in Barcelona. The entire city has party. So 23rd is the party night. So we will have this 22nd and 23rd, 2 days, and then we go for partying. So, and then this is, so all night long. So it was very successful the first 2 years. Again, many people are coming from different parts of the world. So I hope some of you will be interested to start to work on these issues. So I'm sorry about 5 minutes, but I think I started also a couple minutes late. Thank you. Did you measure the decibel? Just kidding.
I don't know if I can. Let's see if we have any questions from the far end.
Looks like the far end's already leaving.
Wondering when you said that many of these things could be quite slow moving and might take time to for the signal or the information to propagate quite a while.
Yes.
But the actual things themselves, I'm sorry if this sounds very naive.
No.
But the actual things, would they be also shorter lived? I mean, would the devices be more at the nano level? Would they persist for a very long time? Like
I think also here is another misunderstanding. People, they think that everything must be like nanoscale. In other words, a human body is a nanomachine, composed of tons of nanomachines. It doesn't need to be very, very tiny, and then say, oh my God, where will I find it? Or you can create tanks and, you know, all these computers with the nanoscale components. Everything is nanoscale, but it doesn't need to be nanoscale. And the components can be. And also you can have these nanomachines that small that you can inject into the body. They can create a network of these nanomachines. So think bigger than just, everything must be very, very small. So of course, when you have these nanoscale components, you will have much more sophisticated processing, memory, and sophisticated communication, information capturing. Those are the advantages. That's what all these AI people are trying to mimic the humans and all that, cognitive sciences. So here's a good opportunity for you with these nanotechnologies. Indeed, you can create this fine granatory of these behavior, of the human behavior, natural behavior.
Any other questions?
A quick question.
Yes.
This is very eye-opening. I think it's very exciting.
Thank you.
And I just
Some people don't think that way. They think it's already done equalizer. Go ahead.
I think the first of nanoscale cells and other things, it seems to me that it's very easy for them to breed. So what's your and other people's thought on how to do the failures?
So
Protein is just...
bravo. In fact, I agree. That's like one of the issues. Like I put one of the slides like reliability, and also the survivability, and when they die or when you lose them, or also the nanomachines fail. We are not there yet. So we want to just create a nanomachine. Really, here's an example. We have this FET project. It's called Future Emerging Technologies in Brussels. So I told these people, we were since 1 year we were working on this. So I told them that can we do 3 nodes? They were laughing at me. 3 like sensor, like nano sensor devices, do some communication. They said we will be happy if we have 2, and then all they do is a nano antenna, nano transceiver, sending something here, and then we will capture in 3 years. He said, what are you talking about? And that's the thing. But now what happens is, this is typical over-exaggerating things. So I was in Saudi Arabia, and I was, I visited this nanotechnologies group. There was this guy, we already have it. And I was thinking, wow, it's bravo, Saudi Arabia, we already have it. Of course he was exaggerating. They don't have anything. So if anybody tells you there is a nanomachine, be skeptical. They have component, yes, nanosensor or nano whatever, but not the full-blown machine. Like my colleague has nano battery, like ZL Wang. He's like good, as I said, but he's still testing these batteries. So we developed a model mathematically, what will be the power consumption, etc. theory, and then we work with him to show that it's really mathematically also true what he's measuring. But it's not out there yet. It's not like everybody buys them. It's not. There's a long way to go. So this is like, in my opinion, 30 years of direction, really. So, if I survive, then I hope I will see some of these things. But this will dominate, trust me. People, they don't do all these things, especially young people, they move slowly to this area. I expect that in 3 to 5 years, this will be like sensor research. I hope it will not be misused, like sensor research has been misused. So I expect like 50,000 papers in the next 5 years. And the bad thing is, of course, as I told you, I repeat, a lot of people will take terrestrial MAC protocol or an adaptive CDMA, bang, either adaptive CDMA for nanonetworks. Whatever AODV for nanonetwork. Come on, So this will happen. But.
All right, let's thank the speaker again.